So Canada's planning on building boiling water reactors, right? This probably isn't new to anybody here. Like that's the plan for Southern Saskatchewan. That's what they're currently working on getting started, just getting started in Ontario. So where Canada's getting into the BWR game. It's an interesting game. There's a lot of interesting economics and weird stuff when it comes to BWRs and how they're managed. So we're going to go over it. We're going to go over some of the weird stuff when it comes to BWRs in this lecture. So I'm just going to do a quick recap of like what is a BWR, because this will help kind of like conceptualize some of this. So a boiling water reactor is similar to a pressurized water reactor or a can-do reactor, and it's using water as a coolant. In this case, it's just light water. The fuel itself is just enriched up to about 5-ish%, whatever. But the big difference here is that the coolant directly goes from the reactor pressure vessel to the turbine. There's no secondary loop. So this ostensibly cuts down on the costs of having that secondary loop or separate steam generators. The reactor pressure vessel itself acts as the steam generator. So it's actually separating the steam from the coolant, and the remaining coolant gets pumped back down to the base of the reactor again, kind of recirculated, and just the steam makes its way to the turbine. But this has some interesting implications, particularly when it comes to managing any kind of radioactive species. You have to be very careful about how things become mobilized within the reactor, because it's going to go right out into your turbine hull. And so through very careful chemistry, we've gotten very good, very, very good at managing that. But we're going to talk about some of those aspects when it comes to corrosion, as well as some nasty things that can occur if things aren't controlled corrosion-wise. So I'll say up front, a lot of these slides I have pulled from a lecture given by the NRC down in the States. So the Nuclear Regulatory Commission in the States, they had a really, really good lecture on the topic I want to primarily talk about today, which is intergranular stress corrosion cracking that can occur in BWRs. So I've directly pulled slides from them. So I'm not making any kind of like illusions about that. It's at the bottom. So it's not fair use. I'm using this just for teaching purposes. All right, so let's go over a little bit of history here, because I think this kind of helps to put things in perspective for what's gone on here historically. Prior to 1974, there were some issues with this kind of phenomena. But they were primarily driven either by like contaminants, which were pretty obvious, or some other, I think it was the fuel cladding itself. Back in the day, instead of using zircaloy, we were using stainless steel, and that had some problems as fuel cladding. But whatever. Starting in 1974, though, we started to see a phenomena within the worldwide fleet of BWRs, which was this intergranular stress corrosion cracking. And initially, this was showing up just in these narrow feed channels, this narrow piping. And this kind of started this general thought process of, this is only a phenomenon limited to narrow piping. And there were some reasons why at the time this was kind of believed to be the case. This was so serious, though, that similar to what can-do reactors experienced with hydrogen embrittlement within the zircaloy pressure tubing we talked about earlier in this course, this was kind of a similar emergency where like, the material that we put in here that we thought was going to hold up is not holding up. So the main culprit here was 306 stainless steel rather than the zircaloy pressure tubing for can-do reactors. But we were seeing this intergranular stress corrosion cracking. We saw this then kick off in 1978 with larger diameter tubing. This was first noticed in Germany. And then later we saw other issues cropping up with alloy 600, which we're not going to talk a lot about today, but that had its own campaign. Alloy 600 saw kind of infamous within the nuclear industry, in the sense that there's a lot of issues that have been had with it when it comes to steam generators. So Canada does not use any alloy 600 in our steam generators, and partially because you can run into a lot of problems. Not really what I want to talk about in today's lecture, but I just want to underline that like there's a whole bunch of other stuff on alloy 600, could be its own full lecture talking about issues with that alloy.
Sorry, what is ISI?
Yes. I think inspection. That's a great question. I actually don't remember. I actually don't know what the ISI inspection, something. They do inspect everything, basically. They had to go through all channels and check to see if this was occurring. And then continuously check on it on a particular basis. So the NRC in the States mandated that on a particular schedule, largely based around the refueling of the reactors, that checks had to be done for this phenomena because it was so serious at the time. So big deal. Now, in 1982, this was then the sort of the most notable version of this, which was this cropping up in the largest diameter tubing, and this was in the States domestically. So it was a major red flag that something had to be done like immediately. So let's do a little quick recap because we did talk about intergranular stress corrosion cracking somewhat. Well, we talked about stress corrosion cracking, we talked about intergranular corrosion. Let's just kind of recap this phenomena though before we continue. So intergranular stress corrosion cracking involves corrosion, the actual cracking of the grain boundaries, usually after they become sensitized, but not necessarily sensitized. So again, that process of sensitization is when you're forming those chromium carbides at those grain boundaries that become brittle, and then you can get cracking along them. And so that also ends up depleting chromium from the surrounding area, and then making this area surrounding where those chromium carbides have formed more susceptible to chemical attack. So in this case, this sensitization occurs in this kind of temperature regime of 425 to 815 degrees Celsius when it comes to austenitic steels, which 304 stainless steel is an austenitic steel. And so this is where you can have this kick off. So the biggest issue for this, at least initially, was largely our old culprit welding problems. It's not going to be the only thing we're going to talk about today, but bad welding can do a real number on things. So if you remember before from earlier in the course, we talked about the welded area creates this kind of heat dispersion throughout the surrounding alloy. And what this can do is this creates a series of regions kind of based on what temperature profile the rest of the alloy experienced. And what can have happen is a certain distance out from that weld, you can get areas that have become sensitized. So those grain boundaries concentrate in chromium, and they can become more easily attacked chemically. So we call this region the HAZ, so heat affected zone. So when it comes to what that looks like, you can have then corrosion occurring through there. So there's our old friend, the stress corrosion cracking diagram. So I think I tested you all on this on the midterm. I absolutely did. Strain, susceptible material, and corrosive environment. We're going to talk about all three in today's lecture, specifically when it comes to BWRs. So we're going to get nice and into the weeds on this. So when it comes to intergranular stress corrosion cracking, this is occurring again at these grain boundaries, and often when it comes to after they become sensitized, but not necessarily always. So let's kind of look at what that heat affected zone kind of occurs, how that ends up happening. So let's say you've added a weld to your piping. You're installing some 304 stainless steel. You're a contractor working on one of these reactors, and this is a pipe that you've installed. You welded it, sort of closed in some way, or onto something else. And that zone there will then create a sort of an area around the actual weld itself that'll become susceptible to this intergranular stress corrosion cracking, and we start to see those cracks forming along that area. So again, that heat affected zone, part of what's happening here, remember that diagram has to involve some kind of stress, not just chemical attack. There's an actual stress attack as well. And the way in which that primarily presents itself is this axial stress. So the kind of inherent stress that comes with the pipe itself being kind of pulled apart ever so slightly, that tensile stress, that axial stress. And so you can get these fissures that occur along that heat affected zone. So these long lines running through that area of the actual pipe. So sensitization and susceptibility. So sensitization equals the chromium carbides forming. So again, that classic method in which you form chromium carbides and there's the area is depleted. But susceptibility is an alloy that's susceptible to stress corrosion cracking. Here's an important distinction. Susceptibility is not necessarily sensitization. Yes, things being sensitized often makes things worse when it comes to this phenomenon of intergranular stress corrosion cracking, but not always. We're going to talk about different mechanisms for how this can initiate that don't have anything to do with sensitization. So be very kind of careful with the terminology. So there's kind of a fun fact here that apparently in sensitized alloy 600 is actually more resistant, supposedly, to the stress corrosion cracking. So yeah, I'm not going to get into that. We're not using that as an example, but just really hitting home that sensitization is not necessarily the same thing as susceptibility. Okay, so it's kind of, again, just a recap here, those grain boundaries, you're forming those chromium carbides. And what ends up happening here is that is going to be heavily controlled by a number of different constituents of the metal. So 304 stainless steel is primarily where we saw this issue. And so one of the things that controls that is the actual carbon content within the stainless steel. So there's kind of a bit of a range within 304. And so for those higher carbon content variations of 304, you saw this much, much worse, particularly if welding was taking things off, because you saw much more readily those chromium carbides forming, and so much more readily the attack at those grain boundaries. And so you saw this very obviously when you have a higher carbon content within the steel. This actual particular test was done with nitric acid, but I imagine it holds over in terms of just general vulnerability. So one thing that comes out of this is this idea of a sensitization fault. So this is kind of neat. I haven't really shown one of these yet in this course, but this kind of maybe helps to wrap your head around how this kind of works. So what I'm showing you here is a series of carbon concentrations for 304 stainless steel, and depending on that concentration of carbon, it'll determine at what temperature range and how long that temperature needs to be maintained for sensitization to occur. So let's look at our most extreme case, 0.019% carbon, very, very low. To actually get sensitization to happen in this case, you have to hold it for about 100 hours in a fairly narrow band, right around 500, 600-ish. That's obviously that's not realistic. Like even if you're welding something, it's going to cool out of that range. It's either going to be above it or below it way longer than 100 hours, since you're ostensibly not going to sensitize it. But on the flip side, if you add a lot of carbon, you become very, very susceptible to that. The ranges are much shorter, down to like a minute in some cases, depending on what that is, and very, very susceptible to forming those carbides.
Sorry, so are those lines like envelopes then?
Yeah, think of them kind of like envelopes. Essentially, you need temperature if you want to sensitize. If the metal is to be sensitized, you don't want it to be, obviously. But let's say if it is to be, the temperature has to lie within this envelope for the specified amount of time. Does that make sense?
Yes.
Yes. Okay, cool. I'm not gonna pull this out on you, but it's a notion. That's the notion for why does carbon control things in that sense to some degree. So tests on it's ferritic steel, stainless steel, but without chromium depletion. So what happens if you don't have actual chromium depletion? Turns out that's actually what's driving things. So there's cases where you formed these grain boundary carbides, but you haven't necessarily depleted chromium from the surrounding area. And in those cases, you don't see these same really, really aggressive intergranular stress corrosion cracking. So it's kind of it's a mechanism by which you have to have depletion for this to become an issue. And in some cases, apparently, can actually be beneficial to form these carbides ostensibly if you don't deplete chromium. So this is sort of an interesting diagram here. What I'm showing you here is a diagram of this content of the carbon equivalent. So it's looking at looking at the ratio of nickel to a carbon to get kind of an overall carbon equivalent. And then in this case, this is very neat. This is looking at your chromium equivalency. So this takes into account molybdenum. So we haven't really talked about 304 versus 316 very much in this course. They are the two most common stainless steels used in the industry. And the big difference between buying 316 versus 304 is that molybdenum content. So in 316, you add 2% molybdenum, and that usually adds quite a bit of corrosion resistance. Again, not always necessary, and it comes at a cost. But in the case of these boiling water reactor operators, you're laughing if you've got 316 because it's much, much, much less susceptible to attack. And that becomes very obvious when you look at this diagram. you can go to much higher concentrations of carbon, assuming you're in that kind of envelope of what you know, for a 316 steel, without necessarily driving that into granular stress corrosion cracking. And so those failures are mostly seen either in 316 steel that's really high in carbon content, like very, very high, or in 304 with like moderate to high carbon content. So in this case, the 316 really stands out in terms of, again, it's not a panacea, but it's less susceptible to this phenomenon. So there was a lot of component replacements when it came to these small pipes being swapped out for 316. So we're going to kind of take a step back. We've gone over the oh, go ahead. Yeah.
You might not know this, but how much monetary value is the difference between going with 304 and 316?
Can't tell you off the top of my head. It's not like if I'm going to run an experiment in my lab, but let's say I'm going to have Daniel buy some 304 or 316, it's moot, you know, on a small scale. But when you're talking about mega projects on the orders of, you know, what a civil engineer might look at, you start to get into like, it becomes very significant.
Okay.
Obviously not significant enough that you wouldn't want to use it compared to 304 for some of these issues.
Okay.
Right. So if you ran into this, a lot of this, I think the Finnish had a whole campaign where they just said, we're just ripping everything out. And we're going to replace everything we think is susceptible. So different nations took different approaches to this, different operators, but it's less of a headache than having your actual reactor go in. That's for sure.
Monetary value, it's worth it.
It's worth it. Yeah. In this case, it would be, yeah. That's the basic idea. It would be worth it to use it off. Once 304 is in there, then things become a little bit trickier.
Okay.
We've figured out very interesting ways of controlling this, which we'll get into. You don't just need to rip everything in. It's basically the way it goes. We've gotten clever with our chemistry. So to this point, I've kind of touched on primarily two things so far. I've touched on this weld, this residual stress that's being applied. So that's again, that axial stress that you see actually forcing apart the heat affected zone to form those fissures. And then sensitization and everything that comes with that. Again, largely from welding at this point is all we've talked about. Don't get too sort of overwhelmed with this diagram. We're going to keep coming back to this diagram over and over again. It's kind of our like waypoint for going through this subject. But I want you now to turn your attention to the notion of what cold work is and fabrication induced stress. So we're now going to move into talking about these two concepts and how they affect this. So let's start with what cold working is. Sort of most kind of notable example of this is cold rolling or bending. If you bend a pipe without it being, you know, at temperature, then you're cold working that pipe. And one of the reasons that's notable in this case is that you can actually force a mechanical phase change, believe it or not. Mechanically, you can actually, in this case, form martensite. So we talked a little bit about martensite earlier in the lecture when I did that. It's all coming back now. All that steel lecture I did before. Well, why'd I lecture at you for like an hour about steels? This is why. Or else a lot of this would just be completely like just nonsense, dude. But yeah, so in this case, this alpha prime phase, sometimes it's also called the epsilon phase. So this is going to be martensite. This is just an example from a duplex steel. I took it because the figure was really nice. Obviously, this is much more. This happens in austenitic steels too, though. It's just for the sake of finding a nice figure. So essentially, if you're bending or you're going to be applying this sort of the shear stress, you can actually form martensite. So why could that potentially be an issue? So martensite has higher yield strength than austenite. Its yield strength is defined as the maximum stress that will the material will tolerate before plastic deformation begins. So you sort of permanently sort of bend, deform the solid. And what we end up seeing is this cold working ratio versus a martensite analysis. It's much more likely to form 304 steel. So you're much more likely to end up forming that martensite compared to 316. Don't actually ask me why. I'm actually not sure metallurgy why that's the case. If anybody yeah, do you actually know?
Yeah, this one is 316L, right?
It's so low carbon. Yeah.
It's low carbon.
Yeah.
So martensite forms much easier when carbon content is high.
That's right. So it's going to end up having that. So that could be the reason. That being said, I think it also applies to 316 in general, I think. But maybe it is actually, don't quote me on that. In this case, so it could be because you have low low carbon. And we'll talk about why martensite starts to create problems when it comes to carbon. So I think this is, no, we're gonna get to that in a sec. It's the next slide. So what I'm showing you here is is yield stress versus your stress corrosion cracking growth. So importantly, this is not intergranular necessarily. This is just stress corrosion cracking in general. And what can happen is if you have a very high amount of yield stress, usually again due to martensite buildup within your steel, you can actually get transgranular stress corrosion cracking. So cracking right through the actual grains themselves, because this ends up being susceptible to the SCC. So what does that end up looking like? Well, some of the reasons for this is chromium and carbon diffuse much more rapidly through martensite, and synthesization occurs more rapidly. Again, that synthesization reaction is going to be the formation of those chromium carbides at the grain boundaries. And so if you form martensite, it essentially ends up going much quicker through it. And so you can end up kicking off that, say, synthesization much more easily. So solubility of copper in a martensite is lower, and therefore solubility of carbon in martensite is also lower, and therefore carbon is more available for this reaction as well as sensitization. So overall, this kind of gives you a nice plot to, okay, how much of an effect does this make? It can be pretty dramatic. So this is again, I think we're still dealing with 304. In this case, you're looking at martensite being not present versus present in this particular stainless steel. In this case, you can see that with no martensite present, times or temperature-wise, your sensitization is pretty kind of limited. But you have to hold it for a while in terms of hours. So if you put that weld in place, unless the metal is staying hot for for hours, you're probably okay. Look back to, this is crazy, to having martensite present. Look how dramatic this is. This is a log scale. That's massive. So you're now down to, damn, what is that? Minutes. So it can make a really big difference in terms of how things hold up. There's a really good example of this. I hope I put in this lecture of where this played a really nasty role in Sweden. But I think we'll get to that in a little bit, the Swedish example, in a little bit. So cold work increases the propensity for corrosion since additional mechanical energy is placed into the material. So when you're talking about stress corrosion cracking, you've bent your material. Inherently, you've pushed things sort of in ways that are not ideal. And so inherently, you've built up stress in your material. So just all else being equal, you've made it more likely for SCC to kick off. Everything else being equal because you've added stress. So cold work can also cause sensitization through can be synergistically worse. So if you cold worked it and you sensitized it, it's even worse. And then especially if you have martensite, it gets even worse on top of that. So all of these issues compound when it comes to your susceptibility of your material. So if you bent a pipe, welded it, and it had high enough carbon content to form martensite, I don't know. It's you can get to points where things can fail really, really quickly. Like in certain cases, some of these things were failing within a year, or I think one example is only a couple of years. All right, so excellent. I was hoping I kept this in the lecture. All right, this is a nice kind of example of how crazy this can get. So this is an example in Sweden. I don't want to pick on the Swedish. I think they do great work. They offer to give me some free stuff, some free material. So, but they are very notable for having an extensive BWR fleet. So it kind of, just odd-wise, they were going to make some kind of mistake. And in this case, this was with a particular portion of their reactor. So some of the piping in which they bent a tube with no stress relief from heat. Bad news bears. All of that stress you've added to the actual metal, and it's all being cold worked. There's been no relief by adding extra heat to the pipe. In this case, I think percentage-wise, I think there's later on, I think it's actually the percent. Again, it's a 304 steel, so and it's kind of a moderate amount of carbon, and so you've definitely formed martensite by doing this. So how bad was this?
Sorry to interrupt you.
Yeah.
During the manufacturing of a plant, they have to do it bending at the site or,
Well, that's a great question. We're going to talk about, so in some ways, bending is actually a great alternative to welding. And there's reasons why you would really want to, there's welding is okay, bending is okay. It's how you do them. That's the issue. You can weld and you can bend. You just, if you're going to weld and you're going to bend, you have to be really careful about how you weld and how you bend. You can do it with 304 too. 304 is okay to weld and bend with if you're controlling chemistry and you're taking certain steps that we'll touch on later on in the lecture. So to your answer, do you have to do it on the site? I think in this case, it was done at site. And there's ways you can handle that on site. Yes, back in the plant, you can get a part made as such, and you can say, okay, fabricate it in such a way that you have no cold work regions of
they
it.
use elbows, I think.
They use elbows. Yeah, that's very common. I mean, this one was like twisted around like a pretzel. Like you saw, it was like a loop. But just eyeballing it anyway. But yes, elbows is fine, but it's not about the mechanical jig that you're using to perform the bending. It's how you're heat treating it afterwards, and what the composition of the output is. That's controlling it. So intergranular cracking occurred, believe it or not, surprise, surprise. And then the cold work structure with martensite, again, about 4% magnetic phase. So you can actually sort of measure for that somewhat when it comes to that. And this takes the sort of vicinity of the crack in terms of where it was, and few grain boundary carbides. So this is kind of neat, right? Because you don't have synthesization, few grain boundary carbides, but you've completely destroyed it. So that's what I mentioned before. Like susceptibility. This was a very susceptible material. This was bound to fail in its current state, but it wasn't sensitized. Great example of that. So corrosion testing, yeah, indicated no sensitization. So, all right. So looking over here is a leak during operation, stagnant water, the stress relief from heat treatment. So yeah, one of the things they could have done is they could have applied sort of heat treatment to relieve that stress. That would have worked. So the bending radius was really, really high. So 17% cold work in terms, I don't know, relative, that's pretty high from what I understand. I can't quote you percentages on this, but relatively high. And stress at the cracked region excluded residual stress on the concentration from scratches. So it wasn't just scratches, it was the actual stress built up from the actual bend. So looking here, so the transgranular crack actually initiated, which is how this ended up happening. And you bent this whole pipe. And so what does martensite do? It's not sensitized. It can end up kicking off transgranular cracking. Remember that's a slide I showed you before. But once you've kicked off that level of a crack, you're bound to have intergranular cracking. So you started with transgranular because of the martensite, and then that ended up going into sort of a series of intergranular cracks that formed through the actual material. So you can see that network almost like ants, kind of like an ant's nest. All right, so we've talked about that fabrication-induced stress, and we've talked about cold working. So we're going to move now on to radiolysis products and high electrochemical corrosion potential. So electrochemical potential, I should say. Sorry. So two BW water chemistries. So up until this point, I've basically been showing you a horror show, pretty much, right? Like I've been showing you lots of issues. You're probably thinking to yourself, man, BWRs, why would Canada ever want to build one of these things? What a nightmare. Well, it's not, if we were just stuck back in the 70s, I would agree with you. I'd say that it would be a real problem if we were back in the 70s in terms of our chemistry. But our chemistry's come a long ways in terms of how we manage these things. So in 1982 was the first case, kind of 1982, 1983, we ended up coming up with a type of chemical control that we call hydrogen water chemistry. So this is a departure from what was the typical chemistry of the day, which was this so-called normal water chemistry. I guess abnormal, certainly authors like to point out that this is abnormal in terms of how you would actually run one of these days. But at the NWC is still often used as an abbreviation for referring to this type of chemistry. So the big difference here is the concentration of dissolved hydrogen in the actual water. So this has come up before. I've been showing you those diagrams of looking at sort of the basic, the fundamental thermodynamics of these things. If you pump a whole bunch of hydrogen into the system, you will lower your electrochemical potential. Like you will drop it overall if you end up sparging your water with hydrogen. And so that's what they did. And it ended up working quite well when it came to preventing corrosion. So dropping oxygen incredibly low, much lower than what it was at during, under normal water chemistry times. And then overall, the stress corrosion potential, stainless steel corrosion potential ended up being below the threshold for kicking off this SEC. So kind of similar to when I was talking to you before about pitting, and pitting have a particular potential for initiation. This intergranular corrosion is similar in that sense, where if we're controlling our electrochemical potential, we can actually drop it low enough with good chemistry to prevent this from happening in the first place. So this caught on very, very well. So every North American BWR, as of this lecture, I think this was, what year was this? This is a 2010 lecture. So every single one was operating under this hydrogen water chemistry. And a whole bunch of them were operating under a regime that we'll talk about in a little bit. But I don't want to get into what that acronym, the NMCA, means yet, because that comes later in the lecture. So very, very successful, like universally essentially applied. So two anodic reactions. Let's kind of go over why does this strategy work, just to kind of recap things. So our two major anodic reactions that can happen in this case is our metal can dissolve, or we can do something with hydrogen. So this might seem kind of obvious, but if you pump a whole bunch of hydrogen into the water, guess what? Just chemical wise, you're going to have more of that reacting than your metal. You're going to save your metal, basically. Pretty simple. There are two cathodic reactions in this case are going to be oxygen, residual oxygen present, as well as created through radiolysis, as well as hydrogen. Our old friend hydrogen peroxide is back because, again, radiolysis products. So the basic way this works is that it's the combination of hydrogen with these two. We'll talk about that in a bit. So let's kind of look at how this ends up playing out. So this is the concentration of hydrogen peroxide in water versus the corrosion potential. So you can see that for our no H2 present scenario, it goes up really steeply. So at this point, we're well into the region where we could have intergranular stress corrosion cracking. Actually, I don't know specifically at what potential that begins. I'm not gonna test you on that. I don't know it off the top of my head. But anywhere down here, like sub 200, we're usually good, kind of in this sort of range. So you can see by applying that hydrogen concentration, you end up dropping that pretty dramatically, even with relatively high concentrations of peroxide in the water. So in this case, this is going to be applied stress versus the medium failure time. So this is looking at two different cases. One is with this tension applied. I'm trying to see what was the difference here between these two. Oh yeah, sorry, it's the concentration of the of hydrogen present. So in this case, for the triangles, this is going to be concentration of total oxygen. Sorry about that. So total oxygen concentration, you can see if you have about 100 ppm, which is pretty damn high. That's way higher than you would have for normal water chemistry. But I think the authors were just trying to make a point with this slide. Like this is way too high to operate a BWR just in general. But if you compare that to like 0.2 ppm, you can see how much more stress you need to apply to reach failure time-wise. So you have to be it bumps things up by orders of magnitude by changing oxygen concentrations. This is like just kind of to make a point. All right, so how does the hydrogen water chemistry work? So again, I kind of alluded to this a second ago, but essentially what's happening is it's pretty simple. You're just basically having hydrogen react with either oxygen or peroxide. That's it. If hydrogen isn't present, those things will attack your metal. If you have a whole bunch of hydrogen present, it'll combine with hydrogen. That's it. I think I have one more slide kind of going over this in a little bit more detail, but that's essentially what's come down to. So there's a bunch of different things that affect this, notably presence of noble metals. We'll talk about this in a little bit, but that's basically what's actually controlling the corrosion in this case. So stereochemistry, I don't know. maybe this is just kind of beating a dead horse, but essentially you need the proper ratio. So H2O, 2 hydrogens for every oxygen. What do you guess? You're going to need about double the amount of hydrogen for whatever oxygen concentration you have. That's it. That's all I'm saying here. It's just like it's not a one-to-one thing. There's a stereochemistry involved in what's in water. This slide is probably just talking down to everything. So hydrogen water chemistry application history. So it's just some historical basis. So I kind of laid into the Swedish there a little bit, but they actually pioneered this technically. So good for them. They did some feasibility tests to see if it was possible, and then it was properly implemented 3 years later at this sort of really notable Dresden plant over in Michigan or Iowa, I forget which state. Where they actually implemented hydrogen water chemistry for the first time. Oh yeah, sort of following that, we say that era begins. Basically, there's a really great figure where it shows an absolute upswell of basically every reactor operator jumping onto this as the solution once it was discovered. So looking at things, so intergranular stress corrosion cracking initiation versus corrosion potential. So, hey, I guess I was about right, but around 200, sort of sub 200, you end up being in that range where you are almost fine, a little bit lower than that to be safe. So you get to that threshold of a negative 230 millivolts versus the saturated hydrogen electrode. So this kind of gives you an idea of what that looks like. And this is very effective. So there's a bunch of good tests on this. I picked up the one for 304 just because that's mostly what we've been talking about in today's lecture. But essentially what happens is you can actually run a test where you can have crack initiation, like the crack has already begun. You've already started cracking your alloy, and you change the chemistry of the water from normal water chemistry to hydrogen water chemistry, and that crack progression stops. That's really good. Like all that business I was talking to you before about like telluride formation, not being like this was great news to everybody running a BWR. This was, I'm sure, obviously I wasn't alive in the 80s, but I'm sure those conferences around the early 80s were, they were feeling pretty rosy about. Anyway, it would have been bad if this wasn't the case. All right, so how hydrogen water chemistry affects the oxide film. So this is kind of an interesting one. This effect is ostensibly subtle, but it has some notable implications when it comes to dosage rates. So I want to I'm not going to bring up the slide. Well, you know what? I will bring up the slide. There we go. Okay, let's go back to our BWR diagram. So I said this was going to come into play. Remember, this is not a can-do reactor, and this is in the PWR. Whatever happens in that reactor pressure vessel can absolutely make its way to the turbine hull, which is where you need to do maintenance. And so you have to be very acutely aware of what dosage you're exposing your workers to. And so that control over that is much trickier. And so this ostensible small change in what kind of the corrosion products are forming, this kind of crud, as people often call it. So the form of the crud that you're forming actually in the reactor itself, it's forming from these sort of a chromate and hematite to these other phases, hematite or a magnetite or whatever. I'm not going to make you memorize this. Whatever, you're changing the oxides. That can have a big implication for how they hold on to radioactive products within the actual circuit. So this is one of the two notable cases. This is for nitrogen-16. So normally under normal water chemistry, this nitrogen-16 would be stable in the form of nitrate. It would form some kind of deposit, what have you, whatever. But it's going to form some kind of stable product within the actual. But once you switch to hydrogen chemistry, you're then going to form this ammonia or a nitric oxide. And so at this point, nitrite, I think, at this point, these are going to end up being volatile and they're going to pass over to your steam turbine. And again, nitrogen-16 is going to end up being, it's radioactive. And so you will start to dose your workers. So how do you mitigate this? So hydrogen water chemistry is based on the recombination of oxygen and peroxide with hydrogen. However, if you just do HWC alone, again, you're going to start to run into this problem, nitrogen 16. So the way in which this is being mitigated is by adding nanoparticles to your solution, to your circuit. The big one that people use these days is platinum. Previously, there's a bunch of different kind of reactors that use different combinations. I forget who came up with it originally, which company, but they sort of have a patented term for this. Platinum is the kind of big one that's used just kind of on its own, but it's fairly simple what's happening. Essentially, the platinum nanoparticles are catalyzing that recombination of hydrogen with either oxygen or peroxide. So by sprinkling in some of these nanoparticles, you can get away with having less hydrogen, and you can get to the point where you're not changing the form of nitrogen within your reactor itself. Again, the chemistry, right? It's very tricky, kind of keeping everything balanced, right? You kind of swallow the spider to catch the fly to some degree, if that analogy makes any sense to anybody. So that was the kind of solution to this, was by adding these sort of noble metal nanoparticles. The other thing that came up was around, it was around cobalt. Maybe I probably should have put this slide one later. Actually, I'm gonna come back to this in a sec. Yeah, sure. We'll do this slide first. So cobalt 60. We talked about this quite a bit at different points. It's a really nasty gamma emitter and a large portion of what your exposure is going to be once it becomes activated. So cobalt 60 activation should be fine as long as that cobalt 60 is maintained in the actual reactor vessel. It's not long lived. By the time you decommission everything and let it sit there for a number of years, it will eventually decay. But if it's getting out into your turbine hull, now you got, problems, right? So one of the ways in which this is controlled is through the addition of zinc. So in this case, zinc in the form of isotope 64 specifically can be added to so zinc oxide can be added to the actual BWR. And in doing so, essentially it'll end up incentivizing the formation of these zinc iron deposits, these spinel deposits, and those can act as glue to essentially hold the cobalt 60 in place within the actual corrosion products. I don't actually know if cobalt 60 is sitting within the spinel structure or the hematite, but regardless, it basically makes everything it sort of hardens it within the actual pressure vessel, and thus you're not worried about it getting into the turbine hull. They do use these in BWRs as well. They do use zinc as well, but it's a different form of it. It's not zinc oxide. I forget what it is. So this isn't a big deal, but I just thought I would mention here, when you're doing this specifically, you want to add zinc, this depleted zinc specifically. So zinc 64. And the reason for that is if you add some zinc 65, you end up ending up into this issue that everybody brings up. Hope Creek apparently was one of these BWRs where they added just regular zinc to it. And you ended up having activation of zinc 65 to something else. And so, what was it? What's the swallow the cat to catch the spider? Things can, anyway. Lame jokes aside, problems beget problems. Okay, we have a couple more to go over here. So the next one, well, I guess I'll make a quick note. I'm not going to talk about in this lecture irradiation, sort of a flux or applied stress. Obviously, applied stress is coming from like the vessel itself and what those structural components are meant to hold together. And your radiation will, of course, you're running a reactor, so you're going to have lots of radiation. So I'm not going to go into those in terms of like rates of radiolysis, or that's not really, it's beyond what I want to touch on. But I'm going to go over two more points of when we talk about intergranular stress corrosion cracking. I'm going to talk about the role of crevices, and I'm going to talk about the role of impurities. Just making sure I'm doing good for time. I am. We're doing great for time. Oh, yeah. All right. So let's start with, well, actually, I don't know which one I started with. Okay, crevices. So I'm not going to go into this in great detail. The chemistry at play here is very similar to the chemistry we would have touched on before. And so I don't want to kind of belabor the point, but there's there's points within the reactor itself in which components have to come together in a way that can form crevices. And within those crevices, you can get really nasty chemistry occurring, dropping of the pH to the point where you lose, you sort of activate whatever steel you might have, and you can run into some serious problems. So I'm not going to go into this. In this case, this is alloy 600 is often used for these kinds of specialty fittings. And so it often comes up in these cases when it comes to crevice corrosion. It's not limited to alloy 600, but it's often the culprit. Again, I'm not going to go into that in any more detail than just it's a thing that can occur. All right, so let's go on to the role of water quality and the effects of these contaminants and or impurities rather, and what role they can have. So important chemistry parameter for thermodynamic activity of strong acid anions, such as chloride and sulfate, are stable at highly reducing crack tip environment rather than the bulk water conductivity. So the grammar's kind of odd here, I apologize. And basically what's happening in this case is you're having these species, these sort of strong acid anions, so chloride and sulfate, are going to be more stable within the actual crack tip itself. You can imagine how this could be very, very bad news bears for continuation of that crack tip. So water chemistry is an absolute must in terms of purification. When it comes to these things, you do not want chloride in your reactor, period. So they're drawn into the crack tip, and they depress the overall pH. So other anions that can do this, so chromate, nitrate, they're not stable in reducing conditions, and they only have a minimum effect. So that's kind of your sort of basis here. So if you, under these reducing conditions, you're not worried about chromate because it's going to form something stable. You're not worried about nitrate, it's going to end up forming something stable. It's the sulfate and chloride that you need to make sure you filter out. So this is kind of a nice poignant example. Again, I like these sorts of experiments because it really highlights what kind of effect this has if you want to like push things to the limit. So this is looking at, again, I think it's whatever, it's some, I don't even know what the steel is, 533B. Don't ask me, I'm not sure what that is. But essentially it's an experiment where they added a whole bunch of chloride and then they removed it again. So it's only actually, I say a whole bunch, it's actually only 10 ppb of chloride. But you can see how quickly that crack length grew. And then how quickly that kind of, I don't want to call it stopped. It looks like it's still going to some degree. It's not as, you didn't reverse things entirely, but it's a lot less once you remove that chloride from the bulk water chemistry. Thankfully, you just filter, right? You get really, really good filters. So surface conductivity is important. So detrimental anions in this case. So again, sulfate and chloride come up there. I guess phosphate is another issue. I suppose that's the same kind of idea. Little impact nitrate and chromate. Again, they're not going to be stable under these conditions, so you're not going to be able to sort of have them floating around your water. They're going to be forming something. They're going to deposit in some kind of solid formation. Silica, I guess, same thing. Some beneficial ones can be borate and zinc. So remember our old friend zinc I talked about there before? Well, it turns out it actually helps with corrosion. So the mechanism involved is very complicated, is more complicated than I wanted to go over in this lecture. But there's good evidence to show that zinc is actually beneficial to add to your reactor in terms of water chemistry control. Again, I didn't want to go into it, but it's something to sort of note here. So let's kind of recap here. What are some ways in terms of mitigating intergranular stress corrosion cracking in BWRs? You can reduce the stress. Don't cold work your metal. Change or modify your alloy. Maybe you're going to 316, in some way. Maybe you're going to a low carbon variant of 304. High temperatures and a high temperature, a 200 ppb oxygenated water. So instead of using your normal water chemistry, which is what's listed there, that high temperature 200 ppb, remove your oxygen from the coolant. And then in this case, add some hydrogen to prevent that oxygen from attacking your metal. So, well, there's a whole bunch more included in that, but there's a lot of strategies that fall under that umbrella of trying to mitigate this. And so we've gotten very, very good. So a lot of these intergranular stress corrosion cracking problems for BWRs are kind of a thing of the past to some degree. It's sort of something we've gotten a handle on for the most part. which is why Canada feels confident in building, because the chemistry behind operating them is being so well tried. All right, mitigation of BWR piping. So susceptible materials. So a whole bunch of things here. So lower carbon, increased nitrogen within the steel, I guess, also has an effect. So solution heat treatment. So again, that's going to be if you've cold worked a pipe, perform heat treatment on it, redissolve those vulnerable chromium carbides from grain boundaries. Just to kind of point out here, look at the stoichiometry of this. 6 carbon for every 23 chromium. That's not good. Yeah, exactly. Right? Corrosion resistant cladding. So there's very inner diameter, very intergranular resistant weld material barrier. So you can do a weld overlay. We're going to talk about what a weld overlay is in a slide, but this is a really good idea if you have a large welded section, particularly for a large diameter pipe. You almost certainly want to use something called a weld overlay. Actually, just for curiosity, Daniel, do you learn about weld overlays when you did your? No, was that more? Okay, I'm just curious to see if they taught that at the college level. It's or when that would. Maybe if somebody asked you to do this, maybe that's kind of, I don't know. I'm not sure how.
I think more so with pipe fitters.
That pipe fitters. Oh, I guess that makes sense because they're actually the ones who are doing the right. Okay, yeah. It's a so tensile stress. Heat sink welding. So compressive. This is where basically it's kind of an interesting technique where essentially you flow the water through the pipe as you're performing welding on it. So it's actually removing the heat actively as the weld is being applied. Kind of neat. IHSI, induced heat stress improvement. So a compressed residual stress. I'm not going to end up testing you on all these. I may ask you a question where I'm like, give me some examples. You know how I ask questions. Tell me you have some idea of how you would go about this, like that you were somewhat listening to these examples. Hydrogen water chemistry, again, weld overlay. I guess it does double duty for both tensile and susceptible material. Anyway, I'm not going to go over all this, but yeah, I may ask you a question where I want you to list something for me. So, Mehdi, you asked me this question before, and I said I would give you a better answer. Well, here's my better answer here. Could you do it just in the factory? Can you do it on site? You can absolutely do it on site, but you'll want to maybe do something like this. So this is kind of a neat. It seems so simple, but it's an induction coil essentially around the pipe itself as you've bended it. You're actually gliding that across the actual pipe itself to perform heat treatment to desensitize the material or de-stress it. Okay, weld overlays. This is going to be the kind of last portion of this section because I don't know, I think they're cool and they're very it's a very kind of like practical solution to a very, very otherwise tricky problem. I think I'm not going to talk about this slide in detail. The information's all there and it's all accurate, but maybe I should just show you what I'm talking about instead of showing you a slide. So, I mean, it speaks for itself to some degree, right? I mean, this is your pipe that you've fit, and here's your weld overlay. It's going to be a very resistant material of some sort. I don't actually think they use like a 308 or I don't know. I think 308 or something following. Or in this case, what's happening is sure you might have a heat affected zone still that could still be susceptible to intergranular stress corrosion cracking, but you've built this entire structure around that weld to protect it. And when doing the engineering, the mechanical engineering behind this, the way it works apparently is you assume that you have no benefit from the original pipe. So all of its structural benefit, you essentially say you have none of that left. You assume that it's completely going to fail. And then you build your weld overlay around that assumption that the internal pipe is going to completely embrittle and fall apart. And that you've built this around it to maintain its integrity structurally. And I won't go back. If you want to read this, that's fine. But it's it talks about optimal uses in terms of structural credits. Basically, what I was saying. Okay, so through wall crack arrest under weld overlay. So this is I really like this image for kind of showing how effective this can be. If you've chosen the right material that's going to be really resistant to this intergranular stress corrosion cracking, you can see that in this case, the 304 steel or whatever steel is experiencing IGCC has completely stopped crack, has ceased at the area of the weld overlay. So very effective. Okay. So I'm going to do a quick kind of a let's talk about what happens under a severe beyond accident condition. Beyond, I think it's called a beyond design basis accident. I think is officially what the term is, which sounds very benign, but a beyond design basis accident means a very, very, very bad accident. So corrosion of zircaloy under severe accident conditions. So what actually happens to that sheathing of the or cladding or whatever you want to call it of the actual fuel if you're under very high temperature steam? So this is a really nice image, I think, showing this off, taken from a paper here. Sorry, I had cited at the bottom, showing over time how quickly that zircaloy will corrode. And this is at relatively moderate temperatures. Like 950 is not nearly as hot as things in the reactor when temperature continues to increase. And so what's happening here is that you have the rapid generation of hydrogen gas occurring as that zircaloy is corroding under these conditions. And that can then in turn kick off a steam explosion, which is what you would have seen. The results, these here, this is not due to, let's say, a runaway transient in the sense that you're like you had in Chernobyl. These are due to the actual steam explosions from the reactor itself. So kind of this is a nice figure that's often used from a perspective article, looking at how the progress of the accident continues as time and temperature continues on. So initially, you're going to have your actual solid fuel, which is eventually then going to start to crack as it heats up. You're going to start to have corrosion of the zircaloy. You'll then have this kind of bursting of the actual zircaloy tube itself, so damaging of the actual fuel elements, and then followed by that formation of this oxide eutectic, and then followed by melting itself of the actual fuel into corium. Very, very freaky stuff for sure. And this is as things go on. So very serious as the accident progresses. I thought this would be kind of neat. I think this is taken from a recent article that TEPCO put out on the progress they're making in terms of cleaning things up. They've apparently removed all fuel assemblies from Unit 4, as they should have, since there was no fuel loaded into Unit 4 at the time of the disaster. And they're most of the way, part of the way through removing fuel assemblies from the storage fuel bay in Unit 3, what have you. So anyway, things are progressing. I think they've made it a little bit farther. They presented it at a conference I was at a few weeks ago. But anyway, I want to kind of show you, I'm getting off track here. The point of me showing you this slide is to kind of point out that it's these steam explosions that have blown the tops off of these reactors, and that it's the lack of steam explosion in Unit 2 that causes the actual reactor containment building to be in place. So the formation of that steam is very, very important. So here's what things end up looking like. Again, this is maybe kind of a recap of that previous slide with some actual numbers attached this time. So you can have that balloon or bust. Let's just look at the red line to begin with here. This is just if you're looking at pure zircaloy cladding, this is what it's going to end up doing. So at about 800 degrees Celsius, you have your this balloon or bust period. So the cladding temperature will drop a little bit as it kind of expels and expands out into the surrounding area, the surrounding coolant. And as things continue, it ends up hitting around 1500 degrees Celsius, in which you have runaway corrosion occurring. At this point, it's completely exothermic, so the whole thing acts kind of like thermite to some degree, kind of similar, and you're producing hydrogen at the same time. So once you have to do what the Japanese had to do, they vented hydrogen from the reactor pressure vessels. Now that hydrogen is mixing with the surrounded air, and if you have failure of your venting protocols, which they also had during the accident, then that's going to mix with oxygen and you're going to have an explosion. or not mysteriously in the case of unit 2. So what's the way in which you mitigate this? You can apply some kind of accident tolerant fuel cladding. So in this case, you still go through the same go through the same problems, but they happen at higher temperatures and longer time durations. So you buy yourself time in the case of a severe beyond design basis accident. So the most commonly studied coating is going to be this based in chromium, just pure chromium. You add chromium onto the zircaloy, and that has some benefits. This has some benefits. It's mostly being pioneered by Framatome under contract from the DOE since Fukushima. And it does basically what it says on the tin. The chromium itself acts as a barrier for the corrosion. You're going to have some intermixing with the zirconium. Unfortunately, you're going to form some intermetallic phases that are kind of brittle. But ostensibly it kind of works. There are some issues with this, though. If you kind of zoom in on this area between the actual chromium oxide and the zircaloy, you can see this more easily under through some kind of dark field microscope. You can end up seeing the intermixing of chromium and zirconium within these phases. So these long kind of zirconium spindles making their way up into the actual chromium. These zirconium spindles making their way up into the actual chromium, and these can act as pathways for oxygen to shuttle itself down to your substrate. And again, basically rendering the coating not moot, but highly ineffective compared to how it would be. I should note here that in the case of, let's say, chromium or most of these coatings, they will not hold up. They buy you time, but in the case of chromium, you will actually vaporize it. It will volatilize. Same thing with aluminum that we'll talk about in a bit. Eventually, you will actually form a vapor phase if you get hot enough in the reactor. So it's buying you time, though, so you don't end up in the case with, let's say, unit 1, where it basically blew up within a number of hours. Or had a steam explosion in a number of